First here. Uh, yeah, I'm ready for the other semester.
Everyone's so happy.
Right. Okay. So, we've been talking for the last number of weeks about the theory of quantum trajectories, and this was really motivated as a way of thinking about open quantum systems and thinking about a way of conceptualizing what's going on in an open quantum system in terms of a measurement model. But in some sense, the quantum trajectories in that context are figments of our imagination. They are simulations of potential measurements that could have been done, and with appropriate averaging over the measurement records, we can then recover, say, the solution to the master equation that is telling us about an open quantum system. But the theory that is developed is also useful in the context where you actually do the measurement, and then you want to be able to study how the state of the system evolves as a function of time conditioned on the measurement you're doing, okay? We have that formalism, we've been developing it. But, historically it was thought of in different contexts. There was a separate sort of theory about continuous measurement that was later connected. I think we now, it's all, quite straightforward in terms of our current ways we now understand and think about CP maps and Markovian systems and so forth, but it took us a while to get there. But of particular interest is what we were talking about last lecture, where in some sense we think about the measurements as continuous measurements that are where we have some very weak measurement of the system through the probe that we are measuring, and we think about our quantum trajectory as a kind of more continuously evolving thing rather than discrete jumps having to do with clicks that give us quite a bit of information, okay? And we discussed this last time as a potential, say, unraveling of the master equation, where the measurement that we thought about was a kind of homodyne measurement. It could also be something about heterodyne that's related to yet another kind of unraveling. The story of quantum state diffusion that was initially studied back in the 1980s by Nicolas Gisin was really later understood to be another unraveling of the master equation from the point of view of heterodyne. It's in the notes. We didn't get to study it. Just one more detail. But what we'll see in a moment here is an idea that's related to thinking about a particular unraveling that we see in a particular probing of a system, okay? And so let me get down to it. These are a set of talks I gave, 2016 probably, at the Les Ouches summer school. It's a lucky place to go. It's there in the French Alps near Mont Blanc, and boy, it's nice. Interestingly, this school, I think it was set up, sort of post World War II, when the French kind of realized that they were, because of the story I understand, de Broglie never really liked Schrodinger's equation, the formulation of quantum mechanics, and so they were kind of behind in modern physics, and they needed to get themselves up to speed, and so they introduced these schools as a way of kind of bringing in people from the community to kind of bring them up to speed. But now they continue today, and they're really a really great resource where you, it's a summer school and you delve into topics. And I was invited some years ago to give a series of talks, and this was kind of what we did at that time. But I'm going to try to talk to you about this today. Maybe we'll talk about lecture 3 if we get there. Let's do it again, okay? So, I mean, the first part of this we've studied together, but I'm just gonna review it here because I think, oh boy, I should have had a clicker. It would be much better, but oh well. This is what we've been studying together and what you've studied in your homework, thinking about the situation where, you know, how we think about generalized measurements. So let's just quickly review this because it's worth thinking about it yet again. We've talked about it over and over again, but it's just worth re-emphasizing it to try to really nail it down, okay? So, you know, our textbook description of quantum measurement is that we have some quantum system. It might be in a pure state, it might be in some superposition of some basis states. And we want to measure in the spaces. So we're going to measure an observable, okay? Here's my classical measuring device as seen on Google Images. And if you search for classical measuring device, this is what you, I don't know, I probably did at some point. So the classical meter is supposed to be such that when you couple these together, it's calibrated such that the meter moves and in a way proportional to m. You calibrate it with these ticks, and then you read off which of the eigenvalues you got. And once you see one of those eigenvalues, then the post-measurement state is that you project onto the eigenvector corresponding to that eigenvalue, and then you renormalize, and the state is the eigenstate that you measured. And we call that the collapse of the wave function, and the Born rule tells us the probability that we're going to see that particular measurement outcome, right? That's our standard textbook quantum mechanics. So the von Neumann theory that we studied is one where we treat the meter not as a classical meter, but as a quantum meter, and the position of the needle is now a quantum degree of freedom, okay? And we initialize it in some way, in some localized wave packet, at some, fiducial state, which is the state where I didn't couple the systems together. And then I couple them together, say, with a unitary evolution that might look like this, okay? So what this unitary is something that acts on the ancilla, that's the meter, that it kicks the meter, so it depends on the momentum of the meter, and then something that's related to the system observable that I'm seeking to measure, and there's some coupling constant chi, okay? And so what this unitary operator does will displace the meter's position by an amount that depends on the value of the observable, okay? And then some proportionality constant that depends on how strongly coupled the system and the meter are, okay? And so if we substitute in to this equation for the state of the system and then just operate this operator on the state, then we replace the observable by that eigenvalue, right? And so now we are displacing the wave packet of the meter or ancilla by an amount proportional to the eigenvalue, okay? And so the meter's state now is correlated with the state of the system, okay? And there's a different translation or displacement of the meter depending on that eigenvalue, and these guys are correlated. Entangled, one might say. And So now the idea is, okay, so now let's, for example, look at the case where my system was in a superposition of two eigenvalues. I'll call them M0 and M1. Okay, so this is my combined quantum state of the whole thing, the system and the meter, and there are two different eigenvalues and two different states of the meter that are displaced appropriately, okay? And so now, if it were the case as kind of sketched with my incredible PowerPoint skills, such that there is effectively zero overlap between the wave packet associated with the 0 and the wave packet associated with the 1, which are the two different wave packets here, then if I were to look at where the wave packet is, so I look at where the needle is on my meter, then there's going to be zero overlap between these, and I'll get an outcome associated with one or the other of those wave packets. And in that case, when I measure where the meter is, I definitely know whether the system was in this or this. And so looking at where the meter is in position gives me complete information about whether the state of the system was M0 or M1, and thus I will collapse my probability assignment to one or the other, okay? And so formally, we can express that by saying, okay, the post-measurement state of the system, unnormalized, that's what this tilde is what I get when I entangle the system and the ancilla together, and then measure the state of the system, say I were able to see it's in this wave packet. And then the post-measurement state, according to this, would be with one of these coefficients, and that's equivalent to projecting onto the eigenvector associated with that eigenvalue of the system. Okay, so that's effectively like doing a projective measurement on the system. And the probability of seeing that outcome is the square of this amplitude, which is also the norm of the post-measurement state without having we normalized it. Okay, so they're one and the same. Right, so we've seen all this. I'm just telling you the story again because it's sometimes nice to hear stories you already know. Okay, so now the point is, what if the wave packet initially normalized was not well resolved enough such that these two different possible translations of the wave packet don't make the needle distinguishable, perfectly distinguishable. So then I have some ambiguity when I see where the meter is. I don't know for sure whether that corresponded to no displacement or the displacement associated with outcome 1. And so that's not going to be a projective measurement on the system, right? So it's a more general object, and so we would call that a weak measurement. And if we ask what is the measurement of the system, what is the state of the system, conditioned on having measured the needle at some position x, then we say, do the same thing, but now I'm projecting the ancilla onto the eigenvector x. That's the position of the ancilla. And that's equivalent to acting on the state of the system with the Krauss operator. The Krauss operator being the partial matrix element of the entangling unitary between the fiducial state, which was the initial wave packet, and the measurement outcome I have when I look at the ancilla, okay? So, right. So the probability, in this case, really the probability density, because this is a continuous variable, so I can't really talk about the probability at a point. I need a measurable thing to talk about probability, but I can talk about probability density. And that probability density is, again, the square of the norm of the post-measurement state before when I applied the Krauss operator to it. And that norm is this, which is another expression of the Born rule, where I'm looking at the expected value of k dagger k, which we call the POVM element. In some arcane language, it's known as the effect. But I don't really use that language anymore. We don't use that language in this class, no. I never said that to anyone. Yeah. Anyway, right. So this is our friend, the POVM. It's a positive operator valued measure. And this really is a measure because it's on a continuous space. So this is where the term came from, right? If I think about the integral over all the measurement outcomes, this is a positive operator valued measure on the space. That's where the term came from. But now we just call it a POVM. Okay. Right. So these are things we know. We know how to calculate these things. All right. So, very good. Blah, blah, blah. Okay, so now let's focus on something that you've seen in your homework, but we haven't really discussed together. Okay. So let's suppose that the initial wave packet of the ancilla, it's the wave function associated with the position space wave function of the initial signal, is a Gaussian centered at the origin, which has a variance of a half. Okay, that's as you square it, then you see that the variance is a half. Okay. Okay, so if that's the case, we can now ask, what are the Krauss operators associated with the particular unitary entangling operation we have? This is the definition, right, of the Krauss operators, the partial matrix element. But this is something we can calculate in this case with some trickery. Because I can think about this object, this operator acts on the ancilla, okay? So it's the momentum operator acting on the ancilla. These are states that are states of the ancilla, okay? So what this does is it translates x by an amount proportion, by amount given by this exponent. And if I act this on the bra, then what it's doing is it's displacing x by this amount. From x's point of view, I can treat this as a number. It doesn't really matter. Ultimately, this is an operator. The Krauss operator is an operator that acts on the system, right? This is a partial matrix element. So the operator is buried in this eigenvalue, but it's really something that will only make sense when it acts on the system state, okay? So there's my trickery. And now this is just the wave function that's displaced before, okay? And so the Krauss operator is a Gaussian in this case because the initial wave packet was Gaussian, representing to the uncertainty the noise in the position of the ancilla, okay? And that noise in the ancilla limits the resolution with which I can see the ticks, and thus the degree to which I can learn something about the state of the system. If I had too much uncertainty in that position, too much noise in that, I would really need a big displacement to be able to distinguish them and have a very strong measurement, okay? So it's useful to factor out this chi and redefine the measurement outcome in units that have the same units as O, right? Now, whatever units O has, this has. If this is going to have O, you do the dimensional analysis. So I can think about now renormalizing so I get the right probabilities, putting in the chi's, and think about the Krauss operator associated with the measurement outcome math cal m, or whatever, scripty m, which is the position of on the meter in units of the observable. Okay, so I've recalibrated, so a volt means some number of angular momentum, okay, or whatever this m is meant to represent. Okay, so this is my Krauss operator, and it's a Gaussian. Okay, so that's interesting. And you know, if we think about that, writing this Krauss operator in the basis of the eigenvectors of O, then if I look at the elements of the POVM, they look like this. Okay. So how do we interpret that? Well, what we can think about this is that we don't really, at this point, this POVM does not correspond to a set of projectors onto orthogonal states in Hilbert space because of the finite resolution here, okay? So there are many different values of m that are consistent with different eigenvalues of the observable. I can't distinguish the different eigenvalues perfectly because my detector has finite resolution. The noise, which was associated with the uncertainty in the position of the meter, limits my ability to know exactly which m it is, okay? Right. Now, one thing to note here is that if the strength of the coupling gets bigger and bigger and bigger, then the Gaussian becomes a delta function, right? And then this does become a projector. It just means that I can always see distinguishing displacements on the meter. But generally, it's not a projector. So if my state is in an eigenstate of m, of O, within this eigenstate, then the probability of seeing measurement outcome capital M, given the state was prepared in eigenvector little m, is Gaussian. I don't get a definite outcome, and it's going to have fluctuations around the mean. That's the noise on the meter, and in these units, the uncertainty in my outcome I'm going to see is set by the meter noise, okay? Which we can call shot noise. We'll call it shot noise for a more clear reason when we think about the meter in terms of something that's more like a probe of a laser probe, okay? But this uncertainty that we see in the measurement outcome is coming from the fact that the meter was not in an eigenstate of position to begin with. The meter had some uncertainty in its position, and then we tried to measure where the meter was, and because of that initial uncertainty in its position, it limited our ability to learn what the eigenvalue is precisely, right? There's another way we can get uncertainty, and that's because it might be that our state of the system was not in an eigenvector of the thing we're measuring, okay? In which case, there's going to be some additional noise that I will see that is due to what we would call projection noise. That's to say, I'm doing them even if chi went to infinity, I'm not going to get a definite outcome because the state was not in an eigenvector of the thing. And so I do projective measurements, there's projection noise. And that's related really to the initial uncertainty in the eigenvalue I'm trying to measure. All right, very good. So now let's think about the measurement back action that happens, okay? So the unnormalized state, after having seen a particular measurement outcome, which corresponds to a position measurement on where the meter is, this is the post-measurement state, right? I multiply whatever the initial superposition is by these Gaussians centered on the particular outcome that I found, okay? So we can think about different limits of this. Okay, so let's suppose that initially the system is prepared in some superposition of M states, okay? So this is the M quantum number, and this is the initial probability distribution, okay? This could be, for example, something we would call a spin coherent state, which is to say the term spin coherent state is a kind of loaded term. But basically the point is here, let's suppose that I prepared a spin, a large spin with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It was a spin 19, okay? And it had, 20 minus 2, 40, 38 different outcomes, okay? And I prepared it with the projection which is an eigenstate of spin along the x-axis. So it had the maximum value of spin along the x-axis. And now I want to measure, so let's draw a picture. Here's a sphere. Here's the z-axis, here's the x-axis, here's the y-axis. And I prepared the state to have it spin along the x-axis. Is that state an eigenvector of, so this guy, I have a state which is an eigenvector of jx with eigenvalue j. J is so j squared on this guy is j plus 1. So it has a magnitude j, and this is the maximum possible value. Is this state an eigenvector of jz? No, it is not. In fact, it has uncertainty in jz. And how would you count? Do you know what the uncertainty is in jx? For this state?
We can kind of use a generalized uncertainty relation.
You can use the commutators.
Yeah. So here is an easy way to calculate this, okay? So we know that if it's a state that's an eigenstate of jx, then it's rotationally invariant around the x-axis, right? Which means whatever this is, it's got to be the same thing as this. And I'm sorry, what I mean to say, this is an eigenstate. I meant jz, excuse me. That's what I meant to write. We know this is true, right? We also know that the mean jz and the mean jx are 0. which means that this is equal to the mean jz squared, and this is equal to the mean jy squared, which are equal.
We mean GY is 0.
I do. Yeah, that's what I mean. Yeah. Whatever. Yeah, thank you.
What he says, not what
Exactly. Thank you. Right. So, with that said, how would you then figure out what this is?
we use the first relationship.
Or exactly, because this is equal to, so j squared is equal to jx squared plus jy squared plus jz squared. And if I look at this state, and look at this expectation value of this, jj plus 1, which is equal to j, the expectation value of this is j squared plus twice the uncertainty in jz squared. Everyone clear why this is j squared? Because this is an eigenvector of jx, right? So then I can subtract this and I get jz squared is equal to j over 2. And so this is equal to the square root of j over 2. Okay, very good. Always a problem with that. So that's what I can think about this. This is a state I can think about that has some spread in, say, its projection of, say, the z component of angular momentum that is like the square root of j. And that would be the projection noise. If I were to try to measure, do a projective measurement, I'm going to get fluctuations. It's kind of like in a coherent state when you have the square root of the number of photons, so there's something going on over there, but anyway. All right, so let's then say, let's suppose that I had an incredibly good meter where the noise on the meter is so tiny that I can resolve very well these different amps. So the spread, this is my meter noise spread, which depends on chi squared, and this depends on, say, the size of the spin. Okay.
So this is like a strong measurement?
This is a strong measurement, right? So this is going to be a projective measurement indeed, and I'm going to get that with that probability. If I have something which has poorer resolution, then, well, the state of the system after is not going to collapse onto a particular eigenstate. And how would I figure out what the post-measurement state is?
It's got to be proportional to the...
It's there, right? So I multiply this by this distribution and we normalize, also known as Bayes' rule. I mean, this is totally classical Bayes' rule. There's nothing quantum about this. And what you'll get is a distribution. Your post-measurement state will have a width that is narrower, that is kind of what you would get by adding these variances like resistors in parallel. That's the formula, because you're adding 1 over sigma squared. And the center will shift over by an amount depending on, and you'll get a post-measurement state that looks like this, okay? Now, this is an example of what we call spin squeezing, in the sense that we've reduced our uncertainty beyond what we had for a coherent state to something narrower, and we did that squeezing in this case through measurement. You could also do squeezing through unitary transformation, but this is a squeezing through the measurement back action. And the degree of squeezing depends on the ratio of the shot noise or the meter noise to the projection noise. When my meter noise is narrower than the projection noise, then I will learn more and I'll squeeze it. Okay. All right. Now, on the other hand, if I had like the crappiest resolution in the world and had almost no coupling at all, then I basically can't, in this case, it's the opposite of the projective measurement. This is the case where the meter noise is huge compared to the projection noise. And in this case, the projection noise is basically negligible compared to the meter noise, okay? And so, in that case, I can replace what the observable was by basically I could treat this like a delta function. In that, I want to take the limit that this looks like a delta function with respect to that, as opposed to the other way, where that looked like a delta function with respect to this, this versus that. And so I just replace what the observer was by what its center is, what its mean value is, okay? And that's the case of very weak measurement. Now, I can then talk about what the measurement outcome is going to be in this particular case as a random variable, which is Gaussian distributed. So this is just a formal way of writing this probability distribution by saying that M is a random number which has this as its mean, and then it has Gaussian fluctuations around that mean with a certain variance, or RMS. Okay, the RMS here is the square root of 2 times chi. So n here is just a Gaussian variable, a normal random variable with mean 0 and unit variance. Okay, and so this is a way of thinking about the measurement outcome as a stochastic variable. And so this gives us now a way of thinking about continuous measurement, whereby here is an example, right? I'm going to do spin squeeze. Yeah.
What was the post-measurement state in the weak measurement? In the extremely.
We'll get there in a moment. Yeah, that's important. But we have to apply the right Krauss operator. But we'll get there in a moment. So what I want to do, because I'm going to want to turn the post-measurement state for the case where we're thinking about this measurement that we're doing over a particular interval of time. Okay, so we're going to think about the measurement now as a dynamical process. So, for example, we want to, say, do the spin squeezing. We want to learn something about the projection spin. And so we're going to somehow encode that into some aspect of, say, a probe of light that passes through the ensemble. And then we're going to measure the light. So the light is the ancilla, okay? And then we're looking at the ancilla through a detector, okay? And we're going to get some photocurrent. Our photocurrent is, well, we can call that X. When we have this kind of macroscopic field, it's kind of like our homodyne detector, where in some sense where there's a beating between the probe mode and something about a signal associated with the scattered photons. That interference together gives me the photocurrent. So I can kind of think about this like the homodyne measurement we were discussing last time. But an important point here is that I want to think about this as a dynamical process. So I'm going to think about a particular measurement that I do on the system as having occurred over some time interval, delta t, okay? I can think about that as the integration time of the detector. Or ultimately, I'm going to make this a differential because I want to think about this measurement as happening over time, as I accumulate more information about the system through the photocurrent I measure happening over continuous time. So ultimately, we're going to take these delta t's to a differential time, but for now, let's just think about it as a finite interval, okay? So I should think about this as a kind of situation where there's a kind of temporal mode of the light, a little wave packet that passes through the ensemble, they become entangled, and then I measure the light, okay? Now, the amount of photocurrent I'm going to see here will be proportional to the amount of time, right? And so I'm going to get a certain current, but then I'm going to get fluctuations on that current to the degree to which I treat this as a coherent state. And those fluctuations go like the square root of the signal, right? So my noise fluctuations, the RMS in the noise, goes like the square root of the amount of time that I measured, because that is related to the number of photons that I counted in that time interval. So with this kind of renormalization, I can think about the signal to noise ratio as something, well, actually it's the noise to signal ratio that I've written here, right? This is going like 1/√2. That's saying something about my shot noise variance. So the point here is that the fluctuations, the noise proportional to delta t, and thus if in dimensionless units there's some rate at which I'm measuring, this is a real cheat with just by doing dimensional analysis to connect these things. But the bottom line point is this: the fluctuations I see in the photocurrent, the amount of noise I see in this photocurrent, assuming a coherent state on this side, will be proportional to delta t. Okay, that's the variance, not the RMS. Therefore, I'm just going to say there's some rate constant that tells me what the variance is, which is the rate at which the signal is coming in, okay? The rate at which I'm measuring things. And we can connect that to what we had in the POVM for the particular case of the Gaussian. We saw that the variance was twice chi-squared. So it's a way of connecting that coupling constant that we saw in the entanglement between the signal and probe to something associated with the rate at which I'm gaining information by just doing this dimensional analysis. And so if you believe that whole thing, then I could just rewrite what we had before, where I just replaced the square root of this by the square root of that. It's just basically a way of relating this to what happens in a certain time interval, okay? All right, so now I want to put this in a differential form, and to do that we need to think about this, what happens in this limit as delta t goes to 0. It's a tricky thing because we're going to have this Gaussian noise, but we're going to have these different limits. And that brings us to the story of the Wiener process, which I hinted at last lecture, okay? So a Wiener random variable is a random variable as a function of time that corresponds to the displacement of a particle that's undergoing a random walk, okay? And if the particle is undergoing a random walk, then it's going to, as we know, diffuse away from the origin, okay, in some random walk. And this is an example of such a random walk. You can't, this is shown on a scale, of 100,000 walks. this looks like a continuous walk, because to really make this a Wiener process, I need to take these walks, limit goes to 0. In that case, what is true is that these particular trajectories are everywhere non-differentiable, but continuous, okay? So you kind of see that in this. It kind of looks jaggedy. And what is true about this Wiener process with using the central limit theorem is that the probability of having a certain W as a displacement, a Wiener value away from the origin, is Gaussian. This is diffusion, right? So the probability that some distance away is a Gaussian with mean 0 and variance t, which is a length of time that it's undergone this random walk, okay? And so the Wiener process is a process with mean 0 and variance t, okay? Now, what becomes interesting is we start thinking about the differential form of this, as say if we look at what's called a Wiener interval. So this is the difference between the value of this random variable W at time t plus delta t and its value at t, okay? Those intervals, based on that probability distribution, are uncorrelated if they are separated by more than delta t. And if those two intervals are within delta t, then it depends on how far away they are compared to delta t, okay? Boy, I never noticed that I switched between the bar and that. This is the same, meant to be the same thing. So if we look at that math, then what it tells us is that in the limit that delta t goes to 0, I call that dw, that's a Wiener stochastic increment, its mean is 0 over the realizations of the statistics of the Wiener random variable, but its square, actually you might think it's mean, but it's true no matter what, for any realization, its square is dt, because its variance is related to the distance. So its RMS is like the square root of dt. dw is kind of like the square root of dt with some randomness about it. And since this is like the square root of dt to differential order, this is 0, okay? So I can think about the Wiener interval, taking the limit, it's a Gaussian random variable which has an RMS of the square root of dt, and then it's a Gaussian around 0. That's how I should think about what the Wiener interval is. Okay. Now, this is actually, as we just described, not a well-defined object, but it's worth just thinking about. If I looked at what the derivative of the Wiener interval, if I define that as something, then based on the same thing, what you can find is that the correlation between that is a delta function. And so we think about the current that's coming out of something that is fluctuating with Gaussian amount in any interval, but completely uncorrelated between any two intervals as Gaussian white noise. Okay? Okay, so now let's return to our stochastic variable associated with a measurement outcome. This measurement outcome was originally associated with, having measured the ancilla. Now we're saying we're measuring the ancilla in a certain time interval delta t, And all we did, we said if delta t was very small, then it's like a very weak measurement. Because as delta t goes to 0, my signal to noise gets worse and worse and worse. And I can use the mean field picture where my measurement outcome is like the mean plus shot noise. And if I take this limit, delta t, and I use this relationship, then what I see is that my measurement outcome in a small differential interval, delta t, is given by what the mean value is plus the photocurrent that's associated with Gaussian white noise. Okay? So this is an example of the measurement record I would see as a function of time if I coupled the meter to the system in this way and measured in continuous time. Okay, I'm going to get to Mosen's question now. So now what's the post-measurement state?
Yeah.
Okay, so the post-measurement state is, as always, we apply the Krauss operator and we normalize. The Krauss operator here is what? It's the Krauss operator associated with the Gaussian. Just what we said was the general form of our Krauss operator when the ancilla initially had some Gaussian noise associated with it. And we relabeled that Gaussian noise in terms of the measurement rate and the time interval, okay? This was previously 2 chi squared, okay? But now I've replaced that by kappa delta t. And the point here now is that I'm going to replace the measurement outcome by this random variable. Because when my measurement is very weak, which is to say as delta t goes to 0, which would make my resolution ridiculous, then I can treat this in terms of the mean field approximation. So what that says is that this is the Krauss operator, okay? And that Krauss operator involves the Wiener noise, the shot noise, and something about the projection. How different is the actual value O compared to the mean value that I think I just measured. Okay, so now let's reanalyze that. So this is what we just wrote down. Everyone with me? So now what I can do is expand out that exponent, the square, and just keep terms no bigger than order dt, okay? And so when I multiply that out, I get this, keeping only the terms, the higher order terms, which will have dt squared or dw times dt are neglected. And now let's just write this again, do a power series expansion. I got to keep terms to order dt, so I got to keep the dw squared term in there. And so that tells me the first 2 terms, this guy combines, this is dt, combined with that gives me an 1/8, and then I have this. So to order dt, this is what the Krauss operator is. And this is the one and only one Krauss operator corresponding to the measurement I do, and it is, as we need it to be, something which is a resolution of the identity. All right, so now let's see what is the post-measurement state. So I just applied that Krauss operator that we just found to the state. Remember, delta O depends on the state as well, because it's the operator minus its expectation value. So it's already nonlinear. And if I look at what the differential change in the state is, I see this, okay? This is, we may not have really absorbed it yet, but this is what we studied last time. This is a form of the, what's known as quantum state diffusion. It's called quantum state diffusion because I have a Wiener random variable which kind of makes the state diffuse in some way, okay? There is this term which is going to try to bring the measurement outcome towards its mean value. But then I have this diffusion term. It's related to the measurement back action. And this is a form of, this is a Schrodinger, a stochastic Schrodinger equation. I mean, it doesn't have a Hamiltonian. We could throw the Hamiltonian is, but it is the evolution of the pure state conditioned on measurement. It is effectively a kind of unraveling, okay? Except that we, the particular way we're learning about the system is through effectively a homodyne measurement, because we sent in a strong probe and then we got some signal on top of it, and what we measured in the detector was effectively an interference between the macroscopic local oscillator and the signal. It was buried in there. It's effectively like the homodyne detection. All right, so this, again, just to show that this recovers a kind of master equation if I rewrite this in terms of a kind of effective Hamiltonian. In this case, there is no Hamiltonian, just have the L-dagger L term, where the Lindblad operators are proportional to delta O. Then it looks like something that's a Lindbladian and then something having to do with the measurement. That if we throw this away, we get this back. Okay, so in order to do that math, we just have to plug those guys in and use the fact that dw squared here is dt. Okay. Now, the way I wrote this, I note now, thing I didn't really realize in 2016 is this isn't really the right division. This really isn't the measurement back action. There is the no jump part of the evolution, which is also, so we have the no jump evolution and the yes jump evolution, and the yes jump evolution has this piece in it, and that piece connected here. So this is not really the quite right division between what is measurement back action, because this is also part of measurement back action. But that's sort of neither here nor there. Okay. Okay, so what do I really want to say? This is an example of what's called a stochastic master equation. The stochastic master equation is stochastic because of the dw. What we see here is the part that had to do with the measurement that we were doing, okay? And that would keep the state pure. we might drive the system with some Hamiltonian. We might also have other decoherence. For example, the light came into that atomic ensemble. Some of that light is going to be scattered in other directions rather than into the forward direction, and we won't collect it. And that diffusely scattered light will cause information loss and decoherence. So we would generally, if we were to really try to model this kind of stochastic equation, we would, in that case, we would have to include the decoherence in it. Okay, so the last thing I want to mention is how we can use this to do what's called a quantum non-demolition measurement, okay? It's an old-fashioned term, a QND measurement, but we still use it. It's really, I mean, any measurement, what demolishes and what doesn't demolish, and what do we even mean by that? But what a QND measurement is our idealization of a measurement whereby we're trying to measure some observable, and after the measurement, if you were in an eigenstate observable, the state is in that eigenstate, and if you find it to be in one of the eigenstates, it's projected into one of those eigenstates. Here's an example of something is not a QND measurement. Suppose I wanted to measure photon number, and I have created a state with in some way, and I want to measure the number of photons in it. If I have a photon counter that counts the number of photons in a particular temporal mode, is that a QND measurement? No. Why not?
The photons are gone.
The photons are gone, right? It's no longer in that state within photons. You've demolished the state. You'd have to somehow, what we did study last semester in the problem that I know you love, which was to say use a Ramsey interferometer which measures the phase shift on an atom due to the light shift associated with n photons, and the phase that's accumulated on the atoms then tells me how many photons I have without actually absorbing the photons. So that's an example of a QND measurement of photon number, okay? So the kind of measurements that we just been discussing, where I coupled have a unitary entangling interaction where the Hamiltonian is proportional to the observable I'm trying to measure, is QND, in the sense that it commutes with the observable that I'm measuring. And so if the system is in an eigenstate, it'll stay in an eigenstate. Okay. So what we want to show is how we do how we can do a QND measurement in continuous time. Okay. So the idea, let's say, I had some observable of the system. I want to measure this. And I'm going to do it through this kind of measurement that we just talked about, this entangling unitary, when we then measure the quadrature or position of the oscillum. And our goal is to measure this. So what we want to show is that the continuous measurement trajectory ultimately will measure that observable and project the system randomly into an eigenvector of O with a probability that's determined by the initial probability amplitude associated with that eigenvector. Okay? So we want to show how a projective measurement ultimately emerges But it doesn't happen instantly because in a short amount of time, I can't tell the difference between these different eigenvectors because I don't have the resolution to do it. I need more time to narrow down what I'm seeing, reduce my uncertainty. The shot noise, the meter noise needs to reduce. So here's how we're going to do it. We're going to ask how different moments of the observable evolve as a function of time, okay? So a small change in that is given by whatever the equation of motion is. Let's forget about decoherence. Let's just say we just are continuously measuring. Then if we go back to this equation, this one up here, and plug that in, the first term does nothing. What matters is this term, and I get this expression, generally. So for example, the mean of O is evolving as I measure. Let's just say my assignment of what the mean is as I gain more current is changing according to this equation, okay? Obviously, if I had no uncertainty in that, I know exactly what this is, and it's not gonna change anymore. It only changes because it's not in an eigenstate of O, and I have uncertainty in O. So if I take that equation and ask how does the second moment go, it depends on this correlation function according to this equation, okay, which follows just from the stochastic Schrödinger equation. And if I then ask how does the variance change as I'm gaining information, plugging in that, and then of course in the stochastic calculus, the madness of keeping the differential squared, I get ultimately this expression. Forget about this yet. Okay? Now, if it's the case, this isn't always the case, that I start as we did with a Gaussian distribution of possible measurement outcomes, like the spin coherent state. And if my measurement is Gaussian, then my moments are all Gaussian. And under the Gaussian approximation, when I have a large enough ensemble, I can get rid of any moments that are 0 for a Gaussian, okay? And so that would be 0 for a Gaussian. And so under that case, we have the following expression. The mean will evolve in a way that it's randomly kicked around depending on what the measurement is, okay? So if I look at this picture, what we said was there's an uncertainty here that was on the order of the square root of j. Now I'm measuring the projection along the z-axis. What I'm going to see is going to be random, and it's going to be random by an amount that depends on the spread in delta jz. And that's what this first equation says. What I see, what measurement I get is going to be kicked around depending on the projection noise. Interestingly, though, the variance in this problem evolves deterministically, even though the measurement is random, because in any time interval, I have a definite variance, which just depends on delta t. The way in which the variance changes is determined. just by the product of those variances. But it's this nonlinear equation, which you can integrate, and you find the answer is this. This is the same thing you would get from Bayes' rule if you just looked at the initial uncertainty multiplied by the uncertainty associated with the shot noise variance of your probe, add those resistors in parallel, you get this change in mix. And so what we see here is that as I look at this longer and longer and longer, ultimately this is going to dominate over this, in which case my uncertainty in O will be squeezed by an amount that's determined by the shot noise resolution of the probe. As it goes to 0, this becomes 0, and I collapse onto a particular eigenvector. Okay? So here is a beautiful simulation that was done by John Stockton 20 years ago. I was on sabbatical back in 2001 at Caltech when they were trying to do this stuff. They really wanted to do the experiment, but this was in Hideo Mabushi's lab when he was at Caltech at the time. And what's being shown here is the following. They're looking at a spin 5 system, or it's a spin 4 system. This is spin 4 system. So the projections can be -4, -3, etc.
Asymptotic.
So this is what the spin could be. It's thinking about its eigenvalues. We're starting in a spin coherent state, and what's being shown here are the measurement outcomes or the measurement record, and then taking the measurement record and calculating what the expected value of Jz is, conditioned on what state you saw, okay? And what we see is asymptotically, each trajectory wiggles around, but ultimately collapses onto one of the eigenvectors. Now you might ask, how the heck does it go beyond ±4 if the maximum value is that?
Shot noise?
What's that?
Shot noise?
Yeah, I mean, this is not the value of the spin, it's the value of the current, and it's the value of the spin that you deduce from what you've seen so far. But that's not necessarily the same thing that's related to the uncertainty that you have on the system. Yeah?
So this is saying that QND slowly becomes destructive after.
Well, it's destructive doesn't mean.
What is the QND part?
QND doesn't mean that there's no back action.
Uh-huh.
QND means if it were an eigenstate, it would not have changed.
Okay.
And it will ultimately collapse on, right? That's what.
So it's like photon is not disappearing; it's still there.
Yeah.
Okay.
And so, but what's interesting here is you see, in some sense, you see the collapse of the wave function. That's overstating the fact, but it's basically the point is that the collapse is taking time. Your ability to decide what the state was depends on what you knew. And ultimately it will, it diffuses around, but it then ultimately locks on as you get more and more resolution, in which case, it stops wiggling as much because there are less possible measurement outcomes that you can see. And which of these it goes to depends on what the initial probability of having this in the superposition. It's really quite amazing, quite beautiful. In between, you haven't collapsed or you have squeezed your uncertainty, which, you will squeeze most probably around 0, but you could squeeze around something else, right? The mean may not be exactly what it was. So I just think this is so cool to see and to think about how you actually would do a projective measurement. A projective measurement is never done instantly. It's always done over some amount of time that you've collected some amount of signal. And, you know, for example, if I have two states of an atom that are separated by energy, I'm calling one qubit state versus the other, 1 versus 0, and I couple this guy to some excited state such that it fluoresces in a cycling transition, it takes a certain amount of photons before I can tell whether it's 0 or 1. I can't tell within a shot noise. So any measurement you do that ultimately you say, I've done a measurement in a basis, happens in time. And it takes a certain amount of time to get the right amount of information to be able to distinguish the different states. And the continuous measurement formalism shows us how to do that over the continuous time. Yeah?
Is the Carl Caves project an extension to this? Like, Carl Caves gave a talk that,
Yeah.
I don't know, has similar features?
Yeah,
It's
I mean,
looking at
you know,
experiments, not
you know,
necessarily.
we worked on this in my group for decades.
Yeah.
And the work that Carl's doing is an extension of that. Really, the whole story there is the question of a continuous measurement, not necessarily of a fixed observable, but of many observables simultaneously.
Oh, right.
And that was the problem that we had set out to explore, and we did some work with Paul Yessen's experimental group, was to say, suppose you drive the system at the same time you're doing this. So that you're just not measuring one observable, but you're measuring different things as a function of time. Can you use the measurement record to deduce what the initial state was? Because if you know exactly what the trajectory is going to be, and you know the dynamics that you're imposing, the only thing you're missing is what the initial condition. That's an example of continuous measurement tomography. And where your complete set of observables are happening in time. You could do the problem where you have very weak back action, then you can think about the strong back action, but this is really the story of it. And what we showed in some initial work with Chris Jackson and Izzat Shojehi, who was the PhD student, who was his DS dissertation project, was that we can do, if we thought about the POVM associated with a particular continuous measurement record, that we could design optimal POVMs for measuring, for doing tomography. But Carl's work has been kind of that on steroids. Yeah. All right, gang. I'm gonna have to run off because I have, I'm not gonna miss the seminar today. It's gonna be a good one, but I have to